Hello, welcome back. This is AMET 104 lecture recording week 4.1. So up until last class, we looked at the simple interest and different examples. So today we're going to go over chapter 10.3, and that's compound interest. So this is going to be a long chapter because there's so many different types of compound interests. So this is probably going to take at least 2 or maybe 3 lecture recordings just to go over this chapter before we actually do any examples. So we briefly talked about the compound interest and what it is and how it's different from the simple interest, but let's go over that again. So the compound interest, so under compound interest, not only the principal generate interest, so does the previously accumulated interest. And so what does that mean? So all other things being equal, so if money invested under compound interest grows a lot faster. Than money invested under simple interest. So obviously, if it generates interest on the previous interest, so it's generating interest on a bigger sum, obviously it will accumulate faster and more compared to the simple interest if everything else is the same. But what does it mean by it accumulates interest on the previously accumulated interest? So let's go over an example to understand what that means. Example, so let's say on the day you are born, your parents deposited, let's say $5,000 in your name in a trust fund account. and the account pays 6% APR in interest, and the interest is compounded. Let's say once a year. Each year. So let's do some calculation here. So let's look at the balance. Let's look at the balance and see how it grows. So on the day you're born, so the day you're born, the account has $5,000 in it, and that's at least given in the problem. And we also know that the APR is 6%, so we know the R equals to 0.06 because it has to be in decimal. So after 1 year, so let's say on your first birthday, how much money do you have in this account? So this is very similar to exponential growth model because it's increasing by 6% for each year. So after 1 year, you should actually have $5,000 multiplied by 1.06 because it's an exponential growth model. Or in other words, this is a 6% growth from $5,000. If this line does not make sense to you, please go back and watch the videos from, about the exponential growth function. I think that's 9.3. So this is growing exponentially. So on your first birthday, you have this much. So if you put this into calculator, you should end up with $5,300. So it already accumulated $300 in interest. So that doesn't sound too bad, right? But what about on the second birthday? So the compound interest works like this. So after first birthday, you have $5,000 and $300 in your account. On the second birthday, you're not only taking the interest from the original $5,000, but you're also taking the interest on that $300. So instead of simply adding $300 on this amount, what you have to do is you are taking this $5,300 in your account and you're multiplying it by 1.06 again. And that should get you $5,618, which is actually a little more than $5,600. So this $18 actually came from the interest of the interest. So we should have we should be able to see that this is already 5,000 multiplied by 1.06. So this whole thing is actually the same as saying, given the 5,000 initial deposited amount or the principal, you're simply taking the 1.06 and you just square this last bit to get this number. So let's use that logic and let's go over to your 18th birthday. So on your 18th birthday, if you use the same logic here you used, it's going to be $5,000, the initial amount, and you multiplied by 1.06 to the power of 18. So when you're putting this into calculator, make sure you do the 1.06 to the power of 18 first before you multiply the $5,000. So by putting this into calculator, you should be able to get 14,271.7. So that's 70 cents. So that's how much you have in your account after 18 years. On your 19th birthday, $5,000 multiplied by 1.06 to the power of 18 should give you 15,128. And do you see that the amount of increase between the first and the second birthday and the amount that increased from the 18th and 19th birthday, even though it's only 1 year difference like this is significantly larger. This is almost $1,000 in difference, whereas this is only $318 in difference. So the exponential, so in this case, the compound interest, you can see that the growth is a lot quicker as the time goes along. So supposedly you didn't touch that money all the way until you're 60 years old. Then that's going to be $5,000 multiplied by 1.06, and you're exponentiating by 60 because it's your 60th birthday. And you'll actually end up with $160,000. Sorry, $164,938.45. So that $5,000 in on the day you're born, if you didn't touch it from this account all the way until when you're 60 years old, this money already grew to $164,938. So that's a significant increase. This thing cannot be achieved by the simple interest. It's only possible because it's an exponential growth, because the interest accumulated is a lot. So let's do the same example and see what happens if the initial deposited amount, or in other words, the principal, was a different amount. So let's keep everything like that. But now suppose the initial deposit amount was $10,000 as opposed to $5,000. So it doubled. So on the day you're born, so the day you are born, you have $10,000 in your account. And on your first birthday, I'm just going to write first birthday, you're going to have 10,000 multiplied by 1.06. And that's going to be $10,600. On your second birthday, 10,000 multiplied by 1.06 to the power of 2. That's going to be 11,236. On your 18th birthday, you're going to have 10,000 multiplied by 1.06 to the power of 18, which is actually 28,543.4. On your 19th birthday, you have 10,000 multiplied by 1.06 to the 19, and that is 30,256. And lastly, let's look at the 60th birthday as well. 60th birthday, you have 10,000 multiplied by 1.06 to the 60, and that should give you 329,876.9. So we can see that if the principal is larger, the outcome, the final value is larger, and that is very intuitive. But some of you may have already noticed, but as you can see, if the initial deposited amount is double, after first birthday, you have exactly the twice as much money in your account. And same goes for the second birthday. Same for the 18th birthday, 19th, and also the 60th birthday. So we should be able to see that it is the principal amount or initial deposit amount is directly correlated to the final value. So principal is directly related to the final amount. So if the principal doubles, then the final amount also doubles. So what about other factors? We can clearly see that the longer you invest for, so the longer the interest accumulates, it's going to yield a lot more at the end. That's pretty intuitive. What about the APR? So in these examples, we only use a 6% APR that was initially given in the problem. So let's work with the APR now. So now suppose when everything else is the same, so the APR is 12% as opposed to 6% we've been working on. If it's the 12%, then if you, obviously the R in this case would be 0.12 in decimal. And on your 18th birthday, you would have $5,000 multiplied by 1.12 to the power of 18. By putting this into a calculator, you should be able to find that this is actually 35,000. Let me rewrite that. 35,449.83. And on your 60th birthday, you'll have $5,000 multiplied by 1.12 to the power of 60. And that should be 4,004,087. Sorry, 487,984.67. So as we can see, when the APR doubles, this doesn't, the amount that we have here not only doubles, but it's significantly larger. So we can see that the relationship between the APR and the final amount is an exponential relationship. So let's go over the formula. Let's establish the formula of the annual compounding. So the annual compounding formula. So the future value F, here this, I said future value, but it could be final value or any other terms we used for the F. It's the same principle. P dollars. In other words, here P is the initial deposited amount or investment account or principal, as we usually call it. And when it's compounded annually for T years, with an APR of R, in this case, R is the APR in decimal, is given as such. F equals to the P multiplied by 1 plus R to the power of T. And that's actually exactly what we did so far. This is also really similar to what we did back in chapter 9.3 when we were going over exponential growth model, because this is exactly the exponential growth model that's actually used in real life situations. So as we can see from this example, on the 60th birthday, we can see the initial deposited amount of $5,000 is the P. And here it was 12% APR. So after you add 1, it becomes 1.12. And the time T is obviously, in this case, on your 60th birthday, it's going to be after 60 years. Hence, this is how you calculate the annual compounding formula. So just to see how the annual compounding increases, let's look at a little table. Suppose that for some T, or a time in years, let's say we first invested the $1,500 and the APR is 4.8%. After 1 year, it becomes 1,572.00. So that's $1,572. Let me put a dollar sign just so you enter the context. After 2 years, this becomes 1,647.46. After 5 years, this amount becomes 23.97. No, it doesn't. Sorry. After 5 years, it becomes 18.96.26. And after 10 years, it becomes 23.97.2. And after 15 years, this becomes 30.47. So obviously we intuitively already know, but this is to show that the longer you invest for, the greater final value or the future value you will receive at the end. So now that we have established the annual compounding formula, let's look at a different type of compounds. Let's now look at a general compounding. So oftentimes, a bank or credit union that offers deposit compounding more than once a year. So annual compounding, as the name suggests, was once a year compounds. But this is more than once a year. Compounded more than once a year. So in other words, this could be semi-annually, or it could also be quarterly. It could be monthly. It could be weekly. It could also be daily. Whatever it is. In this case, the semi-annually obviously is compounded twice a year. Quarterly is 4 times a year. Monthly, it's 12 times a year. Weekly is 52 times a year because there are 52 weeks in a year, and daily it's going to be 365 times a year. And one thing to note is that the more frequent compounding, is better. I'm gonna put a quotation there because people may have a different idea of what better is. So better for the investors. This is because if you compound more frequently, you actually yield more. And let's look at the formula for the general compounding. So it's actually really similar to the annual compounding formula, but in this case, we are going to define a couple different terms like that. So obviously we know that F is a future value. And P is the investment account. This is the capital P is the principal. And the small p, or the lowercase p in this case, is the periodic interest. And here the T is the total number of compounded. So we already know what a future value and the principal is, but let's quickly go over what the periodic interest and the total number of times it's compounded. Obviously, if it's annually, it's compounded once a year. That means if T is 1, in other words, if it's only for 1 year, then you will actually have T is 1. But if T is 2 years, it's also being compounded twice. But what if it's a semi-annually? When it's compounded semi-annually, it's twice a year. And if T is 1, in other words, if it's compounded for 1 year, the capital T is actually 2 because it's compounded twice for that 1 year. If the T is 2, the total number of being compounded is actually 4. You're simply multiplying how many years that it's being compounded by the number of times it's compounded a year. Same goes for if it's quarterly. Then it's 4 times a year. So if T is 1, if it's compounded for 1 year, you will actually end up with 4 here. And if it's compounded for 2 years, you'll end up with 8. And this whole logic follows. So simply, we can actually say that t, in this case, the big T, is defined by the number of years compounded and you're taking that and multiplying by the number of times compounded in a year. Hence the total number of compounding. Now let's look at the smaller p. Let's look at the periodic interest. So the periodic interest is simply found by the APR in decimal and taking that and dividing it by the number of times compounded in a year. So in other words, if APR is given as R, this is a decimal, then for semi-annually, you would have P equals to R over 2. For quarterly, you would have the P equals to R over 4, and so on and so forth. So also if it is, let's say, monthly, you would have the P equals to R over 12. Let's look at an example just to understand how this formula is used, also understand the use of the capital T and the periodic interest. So let me rewrite the general compounding formula. So general compounding formula. And that is given as the final value goes to P multiplied by 1 plus the periodic interest by T. So let's draw a table. So let's say this is T and this is F, and let's define it as $1,500 multiplied by 1.02 to the T. So in this case, let's say this is the quarterly. And we should be able to deduce that in this case is 0.012, and that is the periodic interest. And this should be APR of 4.8%. So the periodic interest is 0.048 divided by 4, so that's 0.012. So for 1 year, it will be compounded 4 times. By plugging in 4 here, you should be able to conclude that this should end up being 1,573.31. For the second year, it's going to be compounded 8 times, and this is now going to be 1904. Sorry, it's going to be 1650.2. And let's say on the 10th year, it's now going to be compounded 40 times because it's quarterly. So you're simply multiplying the number of years by the number of times it's compounded in a year. And that's going to be 2417.2. So let's look at the same thing. Let's look at the same scenario, and let's say the APR is still 4.8%. So in other words, R is 0.048. Then, before then. And let's say now it's done monthly, compounded. Then, because there are 12 months in a year, to find the periodic interest, you're simply taking the R, in this case 0.048, and dividing it by 12. So it's going to be 0.004. To draw the same table, here's a T, and here is the number of times total compounded, and the final value is given as $1,500 multiplied by 1.004 to the power of T. After 1 year, because it's monthly, it would have been 12 times being compounded. And by plugging in here, you should be able to find that it's 1573.61. At the end of the second year, it's going to be 24 times it's being compounded, and you'll end up with 1650.82. And after 10 years, it's going to be 120 times being compounded, and hence you'll end up with $24,021.79. So let's compare it to the previous example. So here we both had the APR of 4.8%. We also both had the same principal or the investment amount as $1,500. The only thing that was different was the frequency of compounding. In the first example, we did a quarterly example, and the second example, we did monthly. So that's the only thing that was different. What you're here to see is that if you compare this number to this number, everything else is the same, but just the number of times it's being compounded. I know it's a very small amount, but you can clearly see that more frequent compounding, in this case, the monthly compounding, actually yield more money at the end than the quarterly compounding. And you can see that the difference between the two gets greater as the years go by. So if you look at the 10 years, with the quarterly, it's 24.17, whereas for monthly, it's 24.21. This may not look like a big difference, but if the APR is greater, and also if the initial investment amount is greater, and also as the time goes by, the difference between the two is going to be greater and greater. Even though this doesn't look like it's a lot, we can still safely conclude that the more frequent compounding schedule yields more money for the investor. So I think I'm going to end the class here today. Next class, we're going to look at the one different type of compounding, which is the continuous compounding. And we're also going to go over the annual percentage yield. And if we have enough time, we should be able to do a few more examples regarding those things as well. Well, thank you for joining the class, and I hope you have a great rest of the day.